So far, we now have three major concepts in our bag of energy. We have work, we have kinetic energy, and we have potential energy. Work we defined as the change in kinetic energy, and potential energy is basically how much is stored up in the system that could become kinetic energy. We are now able to try to put this together and use it in a way that will give us a lot of power in predicting how things are going to move around, even if how you get from point A to point B is a rather complicated sort of thing. So in particular, we want to concentrate on what are called conservative forces. What makes a force conservative? Well, it's ultimately going to have two features. One is that when we're using potential energy with a conservative force, that is, a force that provides potential energy, we're calling it conservative when all it cares about is where you started and where you ended. So, for example, gravitational potential energy was just mgh, and change in gravitational potential energy only cared about your change in height, your initial and final height. So it doesn't matter how you got from high point to low point, whether you went straight down or whether you came down a slope, whatever your height change was, that is how your potential energy changed. This was one of the things that made this a conservative force. All it cared about is how you, the fact that you're at point A now, you were at point B before. This isn't true for all forces. For example, there's the force of friction. If we want to figure out, all right, how much work was done by friction, it's very much going to depend on the path that you took, what length you went over, and whether it was a straight path or not. It doesn't care just about your initial and final position. You might have taken a long, complicated path. So, for example, if again we imagine we are on some sort of incline, and we had a block here, and then we had the force of friction acting on that block, we'd expect the force of friction to be in this direction if it was just sliding down. And how much work was done is going to then depend on what this distance is. The height, on the other hand, of course, will be here. So we can figure out how much potential energy there was. On the other hand, the amount of friction done will change if we were to take a more complicated path to the bottom. So if we were to imagine that instead of a nice flat ramp, we had something much more complicated looking. While our overall distance d would be the same, the path that this object takes is going to be a whole lot more complicated. And you might also think that the force of friction will be changing because the normal force will be changing. Even if we could ignore that, we've definitely changed the distance you have traveled. It's not the same as displacement. So that difference between distance and displacement comes into play when it comes to conservative and, quote, non-conservative forces like friction. The amount of work friction does depends on the distance you traveled. A conservative force only cares about the displacement. So, with that out of the way, we can actually now talk about a very direct relationship between kinetic energy and potential energy. So we could start with some condition where we have a body with some amount of kinetic energy and some amount of potential energy. We can also look at the state of that same body at some later time and see what its kinetic energy and potential energy is. So we'll just look at two different states, an initial and a final state. If all the forces that are acting on the body are conservative, or otherwise not doing any work, such as the normal force, which won't do work when you're moving along a surface, these are the same. Another way of writing that is that we could say the change in kinetic energy is the same as the change in the potential energy. That's basically rewriting this same equation here, again, where all the forces involved are conservative. Now, if we have any non-conservative forces, then we could talk about the work that does. So, for example, maybe I have something sliding down a ramp, but I'm also pushing it as it goes down that ramp, or there's some sort of wind blowing on it that's adding to how fast it's going to be going down, giving it a little extra boost. So I could talk about the work done by that, or there could be friction involved and would be trying to resist that and would be taking energy out of the system. So the most complete form of this equation is if I also add in the work done on the body, which could be positive or negative. So basically it says the amount of energy you have already in the body, both its kinetic and its potential energy, plus whatever work you happen to do, will equal the kinetic and potential energy when you're done. So let's try an example to see how this would go into play. Let's take the following scenario. You have a block at the top of a ramp. You know the ramp is 10 meters long and has an angle of 30 degrees. The block is 1 kilogram and it starts with some velocity 2 meters per second. I want to figure out how fast is the block going when it reaches the bottom of the ramp here. Now, I could do a free body diagram and do all the forces acting on the body. So we'd have, for example, the weight, the normal force, and in this example we'll say that friction is negligible, just for simplicity first time around. So I could then figure out, all right, well, the force of gravity isn't along the direction of this surface, so I'd have to take a component of the force of gravity here, which means that it will have a component of the acceleration in this direction. It'll be over a distance d, and then I use a kinematic equation to figure out how fast it's going at the end. Fair bit of work. On the other hand, we could use energy conservation. So, let's say that the bottom of this slope here is height 0. And so we start at height h, is our high point. How high up is that? Well, since we do have a right triangle right here, and we know the angle, we could find that height. And I see, well, I know sine of 30 degrees is a half. Sine of the angle should be opposite over hypotenuse. So I can use that and figure out that, oh, this thing is up at a height of 5 meters. All right, so I can use conservation of energy, so I'm going to leave the mass terms as m for now, but otherwise the initial kinetic energy is going to be 1/2 m2 squared. Initial potential energy is mg, height of 5 meters. And at the end we have the velocity of the body times its mass half, 1/2 m velocity that we're looking for squared, plus the potential energy, mg, it's at the bottom of the slope, 0. So we see things are going to simplify a bit. This, of course, is just 0. We also see that all the mass terms are going to nicely cancel out in this case. So this is going to tell us that no matter what the mass of the body is, we're going to get the same result. That's kind of cool. So we can just do a little bit of arithmetic, a little bit of algebra, and solve for v final. A little bit of rearrangement, and I find I can get the final velocity in this form, and plugging in 9.8 for my acceleration due to gravity, that is g, and I will get 7.3 meters per second. And of course I could have done this with any other speeds I may have wanted. No matter what, I can get much the same result. That was a lot easier than dealing with accelerations. Now, what if I had to, though, deal with friction? Let's say in this case now that there actually is friction. And kinetic friction in this case, we'll give it a small coefficient, 0.1. So we're still going to start with a height of 5 meters. We'll still end at the bottom at 0. We will need to figure out what the normal force is going to be so we can figure out the force of friction, and we can do that and figure out that the normal force should be equal to mg cosine of theta here, cosine in this case of 30 degrees. And so our force of friction will be mu mg cos theta. So, and how much work is going to be done? Well, it's going to depend on how long the ramp is, which I gave as 10 meters. So, let's use the same energy conservation equation again. We still start out with the same amount of kinetic energy, and again, I'm going to leave mass in terms of m to see that, oh, it'll still cancel out if we're being careful. So, initial kinetic energy is 1/2 m initial velocity squared, that's 2 squared. Initial potential energy, mg height h, which was 5 meters, and then the amount of work done by friction. So we have the force of friction, mu mg cosine theta. The distance is applied, d. And will this be doing positive or negative work? Well, we know that the force of friction is going to be pointing up along the slope as this thing slides down. It should be doing negative work. So it should be taking energy out of the system, negative work here. Makes sense? Final kinetic energy, 1/2 mv final squared, plus the final potential energy, much like before it's at the bottom, so 0. So again, we can cancel out all the mass terms. So we never needed to know the mass of this object at all. That is nice. And again, we can solve for the final velocity. Just a touch of algebra now. So this looks very similar to what we had before for the final velocity, except there's just a little bit of a negative term here under the square root, so it should be a smaller final velocity. And it does, and of course let us not forget the distance it traveled, which I almost did. Plug in all of those values, and you're going to find now that the final velocity is about 6.7 meters per second. So noticeably smaller than it was before, where it was about 7.3 meters per second when it slid down. And I have to say, that was a whole lot easier to do than all of the force, acceleration, and kinematic equation stuff. So this energy conservation equation allows us to do some work rather easily. And this, of course, was for a nice straight path. We could make this a whole lot more complicated. Imagine you were building a roller coaster system, and you'd had some car starting at some high point. It rolls up, down, and comes down to this new height here, and you want to figure out how fast is it going. You definitely don't want to deal with this in terms of forces, since, for example, the normal force isn't going to be constant. The slope is changing as this thing moves up and down, so that's one thing. And you're going to undergo all these curves here, which means circular motion will be involved, which we haven't talked about, which will make things much more complicated. It's not an easy problem if you deal with it in forces. I don't want to do it that way. But if this is a nice frictionless surface, or nearly frictionless, and with a roller coaster system that's other than air resistance, not a terrible assumption, we could easily then figure out this problem in that ideal case of being frictionless, because, again, we can talk about how much velocity it initially had here. We see what height it started at. Then we get down to here. We know what its new height is, so we can figure out, how fast it must be going because of energy conservation. No work was done by non-conservative forces along the way. Remember that the work done by gravity does not care about the path you took, so going over this hump won't change anything. Conversely, we might want to wonder, what if I started with a roller coaster car down here, and I want it to successfully get up this slope and to the top there? what speed do I need for it to even just barely get to the top? Well, with conservation of energy, and again, if we're doing this with the nice frictionless case, that's not too bad. If I know initial and final height, and if it's just barely getting to the top, that means no kinetic energy, it just barely stops up there. I know the final kinetic energy is 0, so I can figure out, oh, how much kinetic energy do I need to make sure that it changes completely to potential energy, and I reach that high point there. So remembering, of course, that the change in kinetic energy is the same as the change in potential energy. In this case, that'll be mg height 1 minus height 2. And if we say at the end we want no kinetic energy, we want it to basically just barely be up there, the best minimum case. So at the end, 0 minus 1/2 mv squared. So I need to figure out how fast that car needs to go. And I'm going to end up getting square root of 2g h2 minus h1. Notice that the h2 and h1 are reversed because I have that minus sign here. And that was a heck of a lot easier than if I had to figure this out in terms of forces. So now you should be able to build your own roller coasters, right? At least in the ideal case of not having to worry about friction or minimizing it enough that you can figure out what you need to overcome various slopes. Now it's not too bad. And also, of course, remember, we also went over this middle slope. When it gets to the high point here, it'll definitely be moving slower than when it was down here when I was traveling up. But we know it'll still have non-zero kinetic energy. It'll still have enough so that we can keep going and reach the top.